Welcome everyone to another Science Olympiad video. This one's meant for Electrochemistry Part 2. Just as a refresher, what we had done last time is we had gone over redox reactions and we also went over reduction potentials. And for today, I wanted to start out by once again summarizing what reduction potentials are. So reduction potentials are basically the tendency of a molecule to gain electrons by basically, transferring it and reducing it. And so, for example, we can have I don't know if that's seen. There we go. We can have, say, Cu2 plus 2E minus goes to Cus. And this would mean that the copper 2 ion is being reduced to copper solid, essentially because it's going from a 2 plus state to a 0 state. On the other hand, we have oxidations, which is exactly the opposite of reductions. So taking that same example into play, let's say we had copper solid and we wanted to move to copper 2. So in this case, that would be an oxidation because it is losing electrons. It's going from a 0 state to a 2 plus state, which means that there are two less electrons in that state. So after we talked about reduction potentials, it's also important to talk about what standard reduction potentials are. So standard reduction potentials are essentially reduction potentials. So I'm just going to reduction potentials at certain conditions. So these certain conditions is like it's 1 volt, 1 molar, and like STP. And something else to know is that every single molecule or species has its own standard reduction potential that's been measured before. And usually when you get questions on these, they'll usually, like the question itself will give you information on the reduction potentials. So now actually moving on to what we're going to talk about today, we're going to start out with a galvanic cell. So a galvanic cell is the logical next step towards electrochemistry after learning about oxidation and reduction. So galvanic cell is essentially where a favored redox reaction is used to generate a flow of current. So going back to like maybe your physics knowledge, you should know that a flow of electricity or a transfer of ions, it creates a current. So for example, in your physics class, you might have talked about, you rub your hands together, you're transferring electrons from one side to the other side, and then you're basically polarizing your surfaces. And that leads to, say you touch something, you'll get static electricity because there's another transfer of electrons. So sometimes the direction of a redox reaction can be determined by estimating the relative strengths of the reductants and oxidants, which most necessarily just means you compare the reduction potentials of those that you think are being reduced and those that you're thinking are being oxidized. And in situations where an electrochemical series is not sufficient to determine the direction of the redox reaction, you can use the standard electrode potential. And so the negative value of a cell potential, which once again, E cell, I don't know if this is being seen. I'll just write it down below. E cell is nothing but the reduction, or like the cell potential of the anode and the cell potential of the cathode, which we will soon learn is nothing but the reduction potential plus the oxidation potential. Not of the same species, is the reduction potential of the species that's being reduced, and it's the oxidation potential of the ion or molecule that's being reduced, or that's being oxidized. So a negative value, if this is negative over here, if it's negative, that would mean that it's a reducing environment. while a positive value of E cell would mean that it is a oxidizing environment. So finally, we're talking about galvanic cells, but I haven't actually showed you what it looks like. And this is a really good picture. I mean, obviously you're going to see this on all your textbooks, but I drew it, and I'm proud of myself for drawing it. So galvanic cells have three main components. There's a salt bridge, which is shown over here, and then we have a cathode, which is this part, and we have an anode, which is over here. So you might be wondering, okay, cathode and anode right here, they have a little bit of a strange definition from when you see it. Usually you associate cathode with a positive and anode with a negative. But here it's almost the opposite, where you're reducing at the cathode and you're oxidizing at the anode. Basically, you're gaining electrons. Basically, more is happening in the cathode, while in the anode, you're losing stuff. So you can kind of think of it as a positive or negative. But if you want to 100% remember this, there's a mnemonic for these. So if you want to remember that oxidation occurs at the anode, you would say an-ox. And if you want to remember reduction happens at the cathode, you could say red cat. An-ox, red cat. So essentially, at the cathode, reduction reaction occurs, and at the anode, the oxidation reaction occurs. And basically what it does is it generates this over here. It generates a flow of electricity across a wire from the anode to the cathode. Now the thing is, I've actually drawn it, the way I've drawn it has a mistake. There should only be 2 electrons over here, simply because there are only 2 electrons that are being transferred. And I'll talk about why. So first let's talk about salt bridge. Why is that important? Well, salt bridge, it maintains electrical neutrality, and so without it, there's an imbalance in charge, and what happens is there's not like equal transferal of electrons, and voltage actually drops to 0. So to keep that voltage, we developed a salt bridge where the anions of the salt, they go towards the anode, and the cations of the salt go towards the cathode. That's pretty easy to remember, right? So over here we can write positive ion in salt goes to cathode, while negative ion in salt goes to anode. Alright, now let's get to how you determine like the anode and the cathode. So in the anode we have zinc solid and zinc 2+, and we know that oxidation is happening here. So if oxidation is happening here, what's the only pathway for oxidation? Well, that's right. You need to go from 0, which is at the zinc solid, to 2+, which is at the zinc 2+. And this is your half cell reaction for oxidation. On the other hand, we have copper solid and copper 2+. So with those two, there's one pathway of reduction, and that's from 2+ to 0, which is what we've written here. Now you might be wondering, why did we say that zinc is the one that's being oxidized while copper 2+ is being reduced? Why is it not that copper solid is being oxidized and zinc 2+ is being reduced? Well, that would be unfavorable for the reaction. And I'll tell you what that means. So, unfavorable. Why does zinc oxidize and copper reduce? So let's look at the half reactions and their reduction potentials. So these are the standard reduction potentials for zinc 2+. And this is the standard reduction potential for Cu 2+. Basically, we're comparing which would reduce. We have a negative 0.76 volts, and we have a 0.34 volts, which is also known as, you could just call it a positive. I just saw that my face was covering that. There we go. There. That's better. Okay. So we determined that in the last class, the higher the reduction potential value, the more likely it is to to gain the electrons, to be part of that transfer. So with that knowledge, you should see that copper 2 plus will get reduced in presence of zinc, which would mean that this would become an oxidation reaction. And how do we write this oxidation reaction? Well, exactly the opposite of what it's shown. Zinc solid goes to zinc 2 plus 2 electrons. And what do we do when we reverse the reaction? Well, we reverse the sign. So this is the oxidation potential. And we're still gonna keep our copper 2 plus as the reduction. Check if it's balanced. How are we going to check that? Well, there's a 0 charge over here. There's a 2 plus and 2 electrons here. That also becomes 0. It's balanced. There's 1 Zn here. There's 1 Zn here. It's balanced. On the reduction side, there's 1 copper on both sides. There's a 0 charge over here. 2 plus 2E minus is equal to 0. And copper solid has a 0 charge. So we're all good. And this is our reduction potential. It remains the same as over here because we didn't change the equation at all. 0.34 volts. Now remember, what do we say up here? The cell potential. The cell potential is equal to the anode, or basically what's happening, the oxidizing potential, plus the reducing potential. And if we just scroll back down over here, look what we have. We have what's happening at the anode, and we have what's happening at the cathode. So we add these two up, and to find the actual equation of what's going on in the entire cell, in the entire galvanic cell, we can add this up as well. We'll get zinc solid plus copper 2 plus goes towards zinc 2 plus copper solid. Here we have our reduction. Not our reduction, that's our oxidation. And then we have our reduction. Then let's add the two values of oxidation potential and reduction potential, and finally get E cell is equal to, well, let's add 76 and 34, you get 110, 1.10 volts. Okay, so we have a positive cell potential. What does that mean? Well, that also means, going back up to what we had learned about, that means that a positive value indicates an oxidizing environment. If you look at the magnitudes of these values, you see that zinc is more ready to be oxidized than copper is to be reduced. So it's going to induce more oxidation. Another way you can actually talk about galvanic cells and spontaneity is to use this to determine spontaneity. So is this spontaneous? Well, we would say yes. Why? If E cell is greater than 0, it's spontaneous. And if you want to learn what spontaneous means, go read about delta G, gives free energy and entropy, and you'll get more of an understanding of what spontaneity means. And hopefully I'll be making a video on that soon as well. So, although we had talked about galvanic cells, we talked about the favorable reaction occurring. We can have the unfavorable reaction occur as well. Let me just scroll down here. So what if we wanted the unfavorable reaction to occur. And that's a very important question, because that brings us into the topic of electrolytic cells. And that is going to be a topic for the next video. So electrolytic cells are essentially the opposite of galvanic cells, where you're going to reverse the battery and you're going to induce the unfavorable reaction, which means that it's not going to be spontaneous. That's why we have this extra, this battery component of it that's going to induce that entire reaction. So if you were to take the example that we're still using into context, we would have an opposite reaction where Zn2 plus and CuS would be our reactants, while Zns and Cu2 plus would be our products, which would actually lead to, if we were to try to do the calculation, you'd still have your oxidation potential. These two would switch, right? So let's go back up to our reduction potentials. We decided that Zn2 plus is not a good reducer, so it's going to oxidize. And we said that Cu2 plus is a good reducer relative to zinc ion. So we decided that this is going to reduce and this is going to oxidize. But in an electrolytic cell, this is going to reduce and this is going to oxidize. In EL cell. Which would mean that we reverse this sign. So if we were to write down E cell for this, we're going to have negative 0.76 plus negative 0.34, which is equal to negative 1.10 volts. Absolutely opposite to our galvanic cell reaction, our spontaneous reaction. So we're going to go into depth more with that in the next video, and I hope you learned something. If you want to learn more about chemistry, more about neuroscience, check out the website. It's always in the description of the video. Have a good one.